So you drag a file into Dropbox or Google Drive. You probably think, okay, my file is uploading. But that's not really what's happening at all. The reality is actually way more interesting. Over the next few minutes, we're going to completely flip how you think about file sync. And it all starts with one core, counterintuitive idea.
Right there, that's the key. This single idea forces us to just toss out our old mental model. So if sync isn't about uploading files, then what in the world is it?
Well, here's the right way to think about it. We're not building a simple file server. We're building a system that's constantly trying to get multiple devices to agree on the state of your data. It's a state reconciliation system. And in this world, the file itself isn't the most important thing. The fundamental unit of truth is something much smaller and way more powerful, a chunk. And that one little shift in perspective, well, it changes absolutely everything.
Okay, so let's dig into that first big idea, chunking. Why bother breaking a perfectly good file into all these tiny little pieces? Well, it turns out it's the only way to solve some really fundamental, totally unavoidable problems with how computers and networks actually work in the real world.
But hang on, before we dive into the how, we've got to ground ourselves in the why. Why can't we just send the whole file back and forth? I mean, it seems simpler, right? The answer lies in a few hard truths about the messy world these systems have to live in. See, any system that's going to survive in the wild has to start here. Networks are going to drop. A tiny 1 byte change to a 1 gigabyte file shouldn't mean re-uploading the whole gigabyte. And tons of users often have identical copies of the same data. A system that just ignores these realities is going to be slow, expensive, and incredibly fragile.
And this is where chunking comes in as this super elegant solution. By shattering a file into these small, content-addressed pieces, we can tackle all three of those realities head-on. If your network drops, you only lose a few chunks, not the whole file. That tiny little edit, it only changes 1 or 2 chunks. And all that duplicate data, we can now spot it and ignore it at the chunk level. And that right there, that's the whole paradigm shift. By chunking the file, we turn this clunky bulk transfer problem into a much smarter set reconciliation problem. The client and server aren't talking about entire files anymore. They're just efficiently figuring out, hey, which of these little chunks are you missing? But how you chop up that file, that presents a really critical engineering trade-off. You could do it the simple way, with fixed-size chunks. But just imagine inserting one single character at the very beginning of a long document. Every single chunk after it would be different. Content-defined chunking is way smarter. It actually looks for natural boundaries in the data itself. This costs a bit more CPU, but trust me, at the scale of Dropbox or Google Drive, they will always choose to spend a little more CPU to save a massive amount of expensive bandwidth. It's not even a question. Okay, so we've got chunks. Awesome. That solves the bandwidth and reliability problem. But we've just created a new problem. How do two machines quickly figure out which of these thousands of chunks they actually have in common? Just sending a full list back and forth would be way too slow. We need a shortcut. This is the next massive hurdle we have to clear. Trying to compare a multi-gigabyte file, byte for byte, over a network, that's a total non-starter. We need a fingerprint, something that can tell us instantly if anything has changed, and just as important, where it changed.
And the answer is this. Just beautiful data structure called a Merkle tree. Here's how it works. You take each data chunk and you hash it. Then you take pairs of those hashes, combine them, and hash them again. And you just keep doing that all the way up until you're left with one single root hash. This one hash is now a unique fingerprint for the entire file. And here's the magic trick, right? Instead of comparing two gigantic files, the client and server just compare their tiny root hashes. If the hashes match, the files are identical. Done. If they don't match, they can just walk down the branches of the tree to instantly pinpoint exactly which chunks are different, without ever wasting time on the parts that are the same.
What this gives us is just incredible efficiency. This divide and conquer approach lets us spot changes almost instantly. It lets us verify just small parts of a file if we need to. And of course, it lets us sync only the specific chunks that are missing. It's a massive, massive win for performance.
All right, so we've got our two main building blocks, right? We have chunking to break down the data, and we have Merkle trees to efficiently compare them. So now let's put it all together and walk through exactly what happens the moment you hit save. So imagine you just hit save on a document. Here's what's happening in milliseconds.
Your machine splits the file into chunks and builds that Merkle tree. Then it sends just the tiny little root hash to the server. The server compares that hash to the one it has, instantly sees which chunks it's missing, and then tells your client, hey, I just need these specific pieces. It's totally surgical. But, and this is a big but, here's where things get really tricky. In a distributed system, you can't assume anything. There's no single source of truth, no global clock telling everyone what time it is. Your laptop and your phone might edit the same file while one of them is offline. Perfect, strong consistency is basically impossible.
So, the system has to make a choice. And the only safe choice is to embrace something called optimistic concurrency. It doesn't even try to prevent conflicts from happening because that would break things like offline editing. Instead, it allows them to happen, but it focuses on being really, really good at detecting them and then showing them to you, the user. It would much rather create a conflicted copy than silently lose your work.
You know, the real test of any big system like this isn't when everything is going perfectly. It's what happens when things inevitably break. So let's see how this architecture we've built up actually holds up under real-world stress. Okay, here's the classic example, right? You're editing a presentation on your laptop, and at the same time, your colleague edits the very same file on their desktop before your changes have had a chance to sync. What happens next? Well, the system's behavior is totally predictable and, most importantly, safe. Because each of those versions has a different Merkle root hash, the server immediately knows there's a conflict. Now, crucially, it doesn't try to guess which one is correct. It saves both versions and then lets you, the human, make the final call. And the most important part? No data is ever silently lost. Ever.
Okay, what about this one? I know you've been there. Your Wi-Fi cuts out right in the middle of uploading a huge video file. Do you have to start the whole thing all over again from scratch? Nope, not at all. Thanks to chunking, this kind of failure is just a minor inconvenience. As soon as your connection is back, the client and server just check which chunks made it through successfully. The sync then resumes exactly where it left off, reusing all those pieces. The system is just fundamentally resilient. It's built right into its DNA.
Okay, so let's bring this all home and lock in this brand new mental model. If you're a developer, this analogy is going to be incredibly powerful for you. These sync systems are basically Git, but for any kind of binary file. The chunks are like atomic commits, and the Merkle trees, that's the super efficient diffing mechanism that makes the whole thing work at a massive scale.
And there you have it. Once you really understand chunking, hashing, and state reconciliation, you start seeing these patterns absolutely everywhere. From blockchains and cryptocurrencies to video streaming services and even how your computer gets software updates. The fundamental ideas are so simple, but when you put them together, they build the very backbone of the modern internet. So, my question for you is, what other systems will you now see in a completely new light?